Okay, in this unit, one of your objectives is to distinguish between the type of substance, ionic, covalent, or metallic, and sometimes the individual bonds within that substance. Let's go ahead and try some practice problems. The first example that I give you is glucose, C6H12O6. It's going to be important that you tell what type of an atom you have within the substance. So carbon is our first thing. We have 6 carbons. Carbon is a non-metal on the right-hand side of the periodic table. Hydrogen, even though hydrogen is on the left-hand side of the periodic table, it is still a non-metal. And finally, oxygen. Oxygen is also a non-metal. Since we have all non-metal atoms within this compound, this most likely is going to be classified as a covalent compound. So we have a covalent compound for our glucose. Now within the glucose, this covalent compound, we're going to have covalent bonds. Makes sense. Covalent molecule, covalent bonds. Let's examine maybe a couple of the bonds. Within glucose, you are going to see some bonds between 2 carbon atoms. Well, carbon to carbon, they're both exactly the same element. They're not going to pull differently. They pull alike. If there's an equal sharing of these electrons or no pull for those electrons, that would be a non-polar covalent bond. You'll also, though, within this compound, have some bonds between O and H, if I went ahead and drew the structure out. If I look between O and H, metal, non-metal, it's a covalent bond, but they don't pull the same. Oxygen actually has a higher electronegativity than carbon. Electrons would be drawn towards oxygen. There is a pull for those electrons, and therefore we would call it polar covalent. Non-polar covalent bonds, and you will have some polar covalent bonds. Okay, that's our first example. Covalent compound with both polar covalent bonds and non-polar covalent bonds. All right, let's take a look at our second example. The second example is copper 2 chloride. So we have copper atoms, Cu, which are metals, and we have chlorine atoms in our compound, which are nonmetals. Whenever we go ahead and bond metals to nonmetals, the metals hold their electrons loose, the nonmetals pull them tight, we're going to get a transfer of electrons to occur. Between metals and nonmetals, you're looking at an ionic compound with ionic bonds. So this is classified as ionic. Now, our next example, Cl2. We have a chlorine atom, and then we have another chlorine atom. That is just 2 nonmetals, a Cl to a Cl. Non-metal to non-metal, this is going to be a covalent compound. And in particular, this particular bond within my covalent compound, I would classify as a non-polar bond. One chlorine does not pull on those electrons any harder than the other one. No pull, non-polar. All right, let's try a couple more. Let's try nitrogen dioxide. You've got nitrogen, you've got oxygen right here. So for nitrogen dioxide, they are both nonmetals. 2 or more nonmetals, well, that is classified as, for us, a covalent compound. Now, within that covalent compound, if you looked at the picture, you'd have a bond between nitrogen and oxygen. Don't worry about the fact that that happens to be a double bond. You're going to learn about that later. What I want you to focus in on is there's a bond between nitrogen and oxygen. Do they pull the same? The answer is no. Electronegativity rises up to the right, fluorine being the highest. Oxygen is going to pull those electrons to it. So within this covalent compound, we know there exists at least one polar covalent bond. This would be a polar bond, polar covalent in the covalent compound. My next one is acetic acid. I have atoms of hydrogen, non-metal, atoms of carbon, non-metal, atoms of hydrogen, and more atoms of oxygen. Since those are all non-metals, we're going to classify this very quickly as being another covalent compound. Now, within this compound, if you went ahead and looked at the picture, and for right now, I'd have to give you that picture. Acetic acid has a structure that looks like the following: a carbon bonded to 3 hydrogens. Whoops, you can't see the third one, but the third one's down below. It's got another carbon double bonded to an oxygen with another oxygen and a hydrogen. Now, if you looked at bonds within this covalent compound, these are all covalent bonds. But what type? Well, I would call the bond between carbon and hydrogen, it is polar, but just ever so slightly. They're almost the same electronegativity, so like mostly nonpolar, barely polar. Between carbon and carbon, well, carbon poles exactly the same as carbon, so that's a nonpolar covalent bond. Between carbon and oxygen, okay, well, oxygen wins. For tug-of-war strength, oxygen's a winner, so that would be a polar covalent bond. Between carbon and oxygen, a polar covalent bond, oxygen wins. And between oxygen and hydrogen, another polar covalent bond. They don't pull the same, so there is a pull overall. So within my covalent compound, I have both polar covalent and nonpolar covalent bonds. All right, one last one, and this one's a little tricky. We have copper 2 sulfate. So I've got copper atoms, a metal. I've got sulfur atoms, a nonmetal, and I've got oxygen atoms, another nonmetal. Metals, nonmetals, this is absolutely an ionic compound. For sure, you should classify it as ionic. However, if I asked you the types of bonds that exist, oh boy, this one's pretty tricky. You've got a copper atom right here that is a copper with a 2+ charge. That is being attracted to a polyatomic ion, the sulfate ion, SO4 2-. So that bond right there between ions, that is absolutely an ionic bond, for sure. A metal and a polyatomic ion, for sure that's ionic. But within the polyatomic ion itself, so I need you to be careful of polyatomic ions. If you wrote out the structure for that polyatomic ion, sulfate is a sulfur that is bonded to 4 different oxygen atoms. And this is what its structure looks like. So this is a bond between a nonmetal and a nonmetal. That's a covalent bond. So in this particular case, when you have, and I'm going to push this up just to give you this rule kind of in general, if you have a metal plus a polyatomic ion, or in fact, if you see a polyatomic ion at all, then you're going to say that you have both inside you, even though you're an ionic compound for sure. But within that ionic compound, there are ionic and covalent bonds within them. You have both types. So be on the lookout for metals that are attached to polyatomic ions. Okay, I hope that helps, and take care.